Hello everyone, my name is Yifang Yin. I'm from National University of Singapore. Today I'm going to introduce our work on multimodal fusion of satellite images and crowdsourced GPS traces for robust road attribute detection. Based on the data sources adopted, existing methods can be roughly divided into two categories, namely the GPS-based methods and image-based methods. It is challenging to detect road attributes from a single data source, as every data source has its own limitations. The figure below shows an example. On the left is a satellite image with heavy clouds. On the right are sparse GPS samples over a narrow road, where little information about the road can be extracted from them. However, prior work on multimodal fusion of satellite images and GPS traces for road attribute detection is very limited, as the two data sources are in significantly different formats, which makes the fusion non-trivial. To solve the issue, we propose to render GPS traces into a sequence of multi-channel images. Our generated multi-channel images from GPS traces are spatially aligned with satellite images on the pixel level. Thus, the two data sources can be easily fused at the input layer by concatenation, where pixel-wise correspondences can be learned. In addition to GPS locations, our work also integrates the rendering of bearing and speed, as they capture not only the spatial distribution of the GPS points, but also the local distribution of vehicles' moving directions and speeds, which are more important for the road attribute detection. Finally, the detection of each road attribute is modeled as an image classification problem. We first introduce how we extract road features from satellite images. We retrieve the information of road networks from the OpenStreetMap. We crop a satellite image at the center of each road segment as the road feature to be passed to the classifier. We set the image resolution corresponding to the zoom level 18 of the OpenStreetMap. And we set the size of each cropped image to 224 times 224, which corresponds to a 134 times 134 meter tile on each road segment. Next, we introduce how we extract road features from the GPS traces. A GPS trace is defined to be a sequence of records associated with timestamps. Each record consists of location, bearing, and speed returned by sensors. Conventional road feature extraction methods first predict the road ID associated with each GPS point based on map matching. Then, given the ID of a target road, statistics such as distributions are extracted from the corresponding GPS records. Thereby, roads are represented by hand-crafted feature vectors. Our method directively renders GPS traces into a multi-channel feature map, given the center location of the target road. Per pixel, distributions for the number of GPS traces, bearing, and speed are extracted, based on which the final road representations are learned by CNNs. We render the GPS points into a 224 times 224 multi-channel image at the same resolution of the satellite images, as illustrated in algorithm 1. For every GPS point, we first compute its corresponding coordinates in the image plane. Next, we update the location channel, the bearing channel, and the speed channel using the following equations. The location channel counts the number of GPS points that are projected onto each pixel. The bearing and speed channels generate pixel-level histograms to describe the local distributions of bearing and speed at each pixel. We further applied kernel smoothing and normalization to refine the images we generated. With a high rendering resolution at 0.6 meter per pixel, the projection of the original GPS points around the road segment can be noisy and sparse. To address this issue, we smooth each channel by computing the moving average over a square kernel with size k. The distribution of GPS traces on roads can be unbalanced due to different road types or locations. To reduce the impact of GPS disparity, we normalize the channels by the equations given below. Here it shows our proposed network architecture. We adopt a network architecture consists of different modules, including a spatial modeling subnetwork with 5 convolutional layers and 2 fully connected layers, a temporal modeling subnetwork with 1 bidirectional GRU layer followed by average pooling and 1 classification layer. Experiments. We evaluated our proposed methods based on 2 large-scale real-world datasets in Singapore and Jakarta. To prepare the datasets, we derived the ground truth labels of 4 road attributes, namely the one-way to-way road, number of lanes, speed limit, and road type from the OpenStreetMap. We removed the road segments without ground truth labels and randomly divide the remaining into 80% to 20% splits for training and testing. The number of samples in the training and testing datasets for the 4 road attributes are shown in the table below. We performed an ablation study on the feature fusion. As we can see, the classifiers trained on satellite images or GPS traces have their own limitations. For example, the visibility of roads may not always be good due to occlusions caused by trees, buildings, or even heavy clouds in a satellite image. The cross-source GPS traces, on the other hand, contain intrinsic noise resulting in incorrectly placed GPS points of the road. The classifiers based on fusion significantly improve the classification accuracy compared to the individual classifiers trained on the satellite images and GPS traces separately. On the road type detection, the classification accuracy has been improved by 11.6% to 14.7%, which demonstrate the effectiveness of our approach. Moreover, on both datasets, the GPS 3D and Fusion 3D outperform the GPS 2D and Fusion 2D in all the cases. This is because the input feature generated from the 3D GPS rendering is more descriptive, as it captures not only the spatial distributions, but also the temporal changes of the GPS traces on the road. We also perform an ablation study on the GPS rendering. We study the impact of the number of channels that we use to render the sensor data into images. Recall that we render the GPS locations into a single channel image that captures the spatial distribution of the GPS points by counting the number of GPS points that are projected onto each pixel. Comparatively, the images rendered from bearing and speed tend to be more descriptive, as they capture not only the spatial distribution of the GPS points, but also the local distribution of vehicles' moving directions and speeds at each pixel. As features extracted from the GPS location, bearing, and speed capture complementary information, the classifier trained on the 7th channel in the last row obtain the best results. Next, we study the impact of the kernel sets we adopted for GPS smoothing. The advantages of applying kernel smoothing to GPS traces are twofold. First, it helps reduce the negative impact caused by sensor noise. Second, the cross-source GPS traces can be sparse in some regions, where pixels on a road can have no GPS points projected to it, especially when we render at a high resolution. We consider kernel sets of 9x9 to be a good choice based on experimental results, and we use this setting in the rest of our experiments. We compare our method to the state-of-the-art methods. Our multimodal fusion solution can be easily integrated with any existing network architectures to train an end-to-end classifier for road attribute detection. For verification, we compare our method to a number of state-of-the-art image classification architectures, including the AlexNet, MobileNet, and DenseNet. DenseNet have been utilized for satellite image processing, such as land use classification in previous work. From the results, we can see that our proposed 2D method performed competitively well with MobileNet and DenseNet, while our proposed 3D method obtained the best result on the detection of all the 4 road attributes. Here we compare our proposed method to 4 state-of-the-art road attribute detection methods. Reference 23 utilized the decision tree as the classifier to detect road attributes from handcrafted GPS features extracted with map matching. Reference 12 utilizes CNNs or GNNs as the classifiers to detect road attributes from satellite images. Reference 27 extracted handcrafted GPS features from map matching, processing GPS and satellite images to separate subnetworks and fused the features before the classification layer. And reference 22 performed GPS rendering without the map matching and fused GPS in images at the input layer. CNNs are adopted as a classifier. As we can see, our method obtained the best road attribute detection accuracy on all the 4 road attributes. That's the end of the presentation. Thank you for listening.